Module 4 will discuss the process for designing pavement for new construction and reconstruction projects. So what do we mean when we say pavement designed for new construction? This would include either new construction or reconstruction projects. So if you have a new alignment, which could be a brand new roadway, or it could be a project where you're going from a 2-lane road to a 4-lane divided roadway. When we say reconstruction, we're talking about roads that have had a base failure, and we have to completely remove the pavement structure from the friction course down to and including the base layer. It could also be a full depth reclamation project. Essentially, if there is a complete development of a pavement system, or in other words, it involves the construction of new stabilization, base, structural asphalt, and friction course, you'll need to use the design process we'll discuss in this module. There are two different methods for performing a pavement design. The AASHTO 93 method refers to the equations that are in the 1993 edition of the AASHTO Guide for Design of Pavement Structures. This method is based on the AASHTO road test, which was a series of pavement tests performed in the late 1950s in Ottawa, Illinois. The results of these tests were used to develop the AASHTO Guide for Design of Pavement Structures, which we're still using today. So since the guide is based completely on the observations of the road test, we know that the AASHTO 93 method is empirical only. The mechanistic empirical design approach introduces a second key factor into the design process, mechanistic. This design methodology is still based on observed pavement performance, but the other part of the method comes from the application of engineering mechanics. The department plans to use the mechanistic empirical design method in the future, but right now we're still using the AASHTO 93 method for designing flexible pavements, so this training will only cover that method. Here is the 1993 AASHTO design equation for flexible pavement. This is the resulting equation from the AASHTO road test from the 1950s. If you read the AASHTO Guide for Design of Pavement Structures, it tells you that there are two important factors to consider with this equation. 1. The equation is a predictor of the amount of traffic that can be sustained before the pavement deteriorates to some selected terminal level of serviceability. And 2. The prediction equation was developed empirically from field observations at the AASHTO road test, with some modifications based on subsequent research after the late 1950s. Again, it's empirical, so it's based on the best fit of the observations from that test. You can find this equation in the Flexible Pavement Design Manual in Chapter 3 in Figure 3.1. As you can see here, this is a busy equation with lots of variables. It looks a little hard to pick out exactly what we're solving for, which is the structural number here. So let's take a look at these variables and make this equation a little less daunting. So reading through the equation from left to right, our first variable is W18. This is the equivalent single axle load, or the design easel, which is the project-specific value. We get this value from our planning office by way of the project traffic forecasting report. So let's take a closer look at this report to identify a few key things that you should always check. On this report, you'll see design information. Here you should verify that the years shown are correct. Also verify the directional split and the number of lanes in one direction. The directional split tells us if there's traffic moving one direction or two. For traffic moving in one direction, such as a one-way road, this value should be 100%. For two-directional traffic, the value is 50%. So for example, a 4-lane divided highway with 2 lanes heading east, 2 lanes heading west, we would look for the directional split to be 50%. The number of lanes in one direction in that example would be 2. The next area on this sheet to check is the equivalency factors. If you remember from Module 1, the equivalency factor is a ratio of the number of repetitions of any axle load and configuration required to cause the same amount of damage as a single application of an 18-kip single axle load. So to verify that the correct equivalency factor is used in the traffic forecasting report for your project, look in the Flexible Pavement Design Manual in Appendix D. Table D3 lists the different equivalency factors for the different facility types. So in the example here, our road is a rural highway, and the factor selected matches the value shown in Table D3 for a rural arterial for flexible pavement. On the next page of the traffic forecasting report, go ahead and verify that the information from the previous page matches here. So check the years and their associated AADTs. Check the directional split factor. Check the truck percentage. Check the equivalency factor. Check the lane factor. And to check the lane factor, you'll need the equation that's found in Appendix D of the Flexible Pavement Design Manual, just underneath Table D2. The lane factor is the proportion of the one-directional trucks in the design lane. As you can see here, there are two variables in this equation, the one-way AADT and a factor called LV. The one-way AADT will come from the traffic report, and the LV variable is a factor that accounts for the number of lanes in one direction. So as you can see here, LV equals 0 when you have 2 lanes in one direction. LV equals 1 when you have 3 or more lanes in one direction. So let's do a quick sample calculation of the lane factor. In this example, we'll look at the first year here, which is 2016. We see in our lane factor equation here that we need the one-way AADT, and we need the information about how many lanes in one direction we have. We will need to compute our one-way AADT by using the value for 2016 shown on our traffic report here. So 7,100 divided by 2 is 3,550, which will be our one-way AADT. Since this example has 2 lanes in one direction, our LV value will be 0. So now we just plug these values into our lane factor equation, and we should come up with the same number as shown in the traffic forecasting report for the year 2016. So let's look at the LF column here, and we see a value of 0.892, and this matches the value we computed, so we're good to go. Okay, so now that we've checked everything in the table on page 2 of our project traffic forecasting report, let's look at the number we're most interested in for our pavement design, the design easel. You can find that value near the bottom of page 2. For this particular project, we see that our design easel value is around 12 million. So returning to our AASHTO design equation, we now know our W18 or design easel value. The next variable to determine is the standard normal deviate, which is noted by the Z sub r. The standard normal deviate is the logarithmic form of the reliability value. Chapter 4 of the 93 AASHTO guide is dedicated to reliability, and in that chapter there are several definitions of reliability. The one that's most suitable for this training states that reliability is the probability that a pavement section designed using the process being the design equation shown at the top of this slide, will perform satisfactorily over the traffic and environmental conditions for the design period. The Flexible Pavement Design Manual provides Table 5.2, which gives us a range of suggested reliabilities based on roadway facility type, and also whether it's new construction or rehabilitation. For our example calculation, since we have new construction of a rural arterial roadway, let's use a reliability of 90%. Looking in Appendix A of the Flexible Manual, we see a reliability of 90% corresponds to a standard normal deviate value of negative 1.282. The next variable to discuss is the standard deviation, which is noted by the S sub O. This is the combined standard error of the traffic prediction and the performance prediction. The department uses a constant value of 0.45, and so that you don't have to try and remember this on your own, you can look in the Flexible Pavement Design Manual, section 2.2.2, and we define it there for you. The next variable to cover is the change in serviceability, noted by the delta PSI. To understand what this is, we need to first talk about the present serviceability index, initial serviceability, and terminal serviceability. The present serviceability index is a scale from 0 to 5, with 0 being the worst and 5 being the best, of the ability of a road to serve the traffic. AASHTO describes this as a measure of roughness and distress, with roughness being the main factor affecting the present serviceability index. Initial serviceability is the condition of a newly constructed road, and terminal serviceability is the condition of a road that has reached the end of its design life. AASHTO suggests using a value of 4.2 and 2.5 for initial and terminal serviceability respectively, and the department has chosen to use these values as well. So, knowing our values of initial and terminal serviceability, we can calculate the change in serviceability, which is the difference between initial and terminal serviceability. The value FDOT uses is 1.7, and again, so you don't have to memorize this information, it's all included in section 2.2.2 of the Flexible Pavement Design Manual. The next variable is the resilient modulus, which is denoted by the MR. The resilient modulus is a project-specific value for the strength of the in-situ soils that your pavement structure will sit on. The resilient modulus value is provided by the State Materials Office for every project. For new construction projects, your geotechnical engineer will need to collect soil samples and take them to the State Materials Office so the staff there can run the laboratory resilient modulus test. If your project has fill sections that are 3 feet or more in height, you'll need to collect soil samples from potential borrow areas. Once the State Materials Office has run the lab tests, they'll provide a memorandum with the test results and a recommendation for the resilient modulus value for your project. So in this example, the recommended resilient modulus is 10,900 psi. One side note about our resilient modulus section in Chapter 5 of the Flexible Manual. Section 5.2.4 discusses a way of obtaining a resilient modulus value from a design LBR value. This section in the manual is really intended for use on off-system projects where lab resilient modulus testing is not possible. The FDOT State Materials Office is the only location in the state of Florida that can run the resilient modulus lab test, and due to the workload for our on-system projects, we just simply don't have the capacity to also run lab tests for off-system projects. So to provide a reasonable way for local agencies to get a resilient modulus value, we've included section 5.2.4, which is the section on resilient modulus from LBR. Table 5.1 is included in this section, and as you can see, the maximum LBR value listed in the table is 40, which corresponds to a resilient modulus value of 12,000 psi. The relationship between the LBR and the resilient modulus is an approximate one, and this is why using a design LBR greater than 40 is not recommended. Another element that will impact your resilient modulus is the clearance between the bottom of your base material and the estimated seasonal high groundwater. I should note that the estimated seasonal high groundwater is the elevation that the groundwater can be expected to rise due to a normal wet season, and it's typically determined by the geotechnical engineer. We've received questions in the past on whether the base clearance is in reference to the estimated seasonal high groundwater or to the design high water that's used in pond designs. So just to be clear, when you're talking about pavement design, the base clearance is in reference to the estimated seasonal high groundwater. So why do we need a 3-foot base clearance? Well, the 3-foot dimension was determined through research and through observed performance experience. The results of that research shows that a 36-inch base clearance was considered adequate for the base protection of most of the subgrades against high groundwater table. Other reasons for providing an adequate clearance between the bottom of the base and the estimated seasonal high groundwater are to help ensure good long-term pavement performance and also to help achieve compaction and stability during construction. So here are the requirements for base clearances. If you have 3 feet or more of clearance between the bottom of your base and the estimated seasonal high groundwater, then you're good to go. You can just use the lab resilient modulus value. If your clearance is between 2 and 3 feet, you'll need to reduce the lab resilient modulus by 25% for your design. And if your clearance is between 1 and 2 feet, then you'll reduce the resilient modulus by 50%. In addition to all these considerations, you should also coordinate with your district geotechnical engineer and your district drainage engineer for projects with high groundwater situations. Okay, so coming back to the AASHTO design equation. Now that we've determined each of the variables in the equation, it's time to plug them all in and calculate our required structural number. Again, here are all the values we just found. Our design ESL is 12,618,000. Using a 90% reliability, we have a standard normal deviate of negative 1.282, and our resilient modulus is 10,900 psi. The standard deviation and change in serviceability are constants, so those don't change. So now we see what the equation looks like with everything plugged in. Our only unknown value is the structural number. So if you were to go through and solve this equation for Sn, you would get 4.5184103. So our required structural number is 4.52, and we'll get into exactly what that means for our pavement design in just a minute. But first, let's take a look at a quicker way to arrive at this number. Now that we know how to do the calculations, let's look at the shortcut for everyday use. So if you want to skip the long equation calculation, you can go to Appendix A of the Flexible Pavement Design Manual. I'd suggest using the bookmarks within the PDF to your advantage when looking for the correct table. So if you expand Appendix A within the bookmarks, you'll see quite a long list of tables. Let's zoom in a little on the Appendix A bookmarks. The design tables in Appendix A are organized by the percent reliability and the resilient modulus value. So looking at the list of tables here in the bookmarks, we can quickly navigate to the table we need for our example. Remember, we have a 90% reliability and a resilient modulus value of 10,900 psi. So for our example problem, we'll need to take a look at table A4A. Let's look at how the design tables are set up. We have the resilient modulus values across the top of the table, and the design easel values along the left-hand side. So once you've navigated to the correct table for your project conditions, based on your reliability and your resilient modulus, you find your design easel on the left of the table and your resilient modulus value on the top of the table, and then find the value in the table where they intersect. So let's say we have a design easel of 1 million and a resilient modulus value of 13,000 psi. You find 1 million easels on the left and 13,000 psi on the top, and look at where they intersect. We see that the structural number associated with 1 million easels and 13,000 psi is 2.81, and that's all there is to it. So now let's look at using the values from our previous example problem. So using the numbers that we found for our previous calculations using the AASHTO design equation, let's find our required structural number using the design tables. So with our example values being in between the easels and resilient modulus values shown in the design table, we'll need to do some interpolations to find our required structural number. So after interpolating between 10 and 15 million easels, and also between 10 and 11,000 psi, we come up with a required structural number of 4.51. So now let's check it against the structural number that we previously calculated using the AASHTO design equation. That value was 4.5184103, so they match pretty well. So now that we've determined our required structural number, we can move on to the next step, which is calculating the layer thicknesses for our pavement structure. To do this, we start with the equation shown here. Your total calculated structural number is equal to the sum of each layer's thickness times its layer coefficient. A layer coefficient is an empirical number that FDOT has developed for each material type listed within the Flexible Pavement Design Manual. For new construction, the layer coefficients are found in Table 5.4. In general, we think of our layers in terms of starting at the top of the pavement structure, so the friction course, and working our way down to the bottom at the subgrade. So layer 1 is typically the friction course, layer 2 the structural course, layer 3 is the base course, and layer 4 is the stabilized subgrade. Now let's take a look at the layer coefficients in Table 5.4. Here's our table for all the different layer coefficients, which you may also hear them referred to as structural coefficients. A couple of things that I'd like to point out here is the layer coefficient values of our friction courses and our structural courses. FC5, which is our open graded friction course, has a structural coefficient of 0. This is because we assume that FC5 provides no structural value to our pavement system. Its purpose is to provide the required friction for the paved surface and to aid in draining the water from the road surface and to reduce tire spray in wet weather. Another thing I want to point out is that our dense graded friction courses offer the same structural value as our super paved mixes, which can be helpful in our pavement designs. So now we know where to look for our layer coefficients, but we should also determine if we have any minimum layer thicknesses. Table 5.5 provides minimum thicknesses of structural course and also minimum base group numbers depending on the facility type or design easels. So for our example problem, we have a design easel of 12.6 million, so our minimum structural course thickness is 3 inches and our minimum base group is 9. So let's look at what base groups are. If we recall from Module 1, there are different base course materials that may have different thicknesses but are structurally equivalent, and they're grouped together to form an optional base group, as shown here. So in a pavement design, you might call out the use of optional base group 9. The contractor would then look at this table, which is also found in the standard specifications, and select a material at a specified thickness from base group 9. As an example, reading across optional base group 9, we can see that 10 inches of lime rock base, which has a structural number of 0.18 per inch, provides a total structural number of 1.8. Likewise, 12 inches of graded aggregate base, which has a structural number of 0.15 per inch, will yield a total structural number of 1.8. So let's go back to our example problem now, and let's look at some things for the layers. Let's start with the stabilized subgrade, since we can go ahead and make some assumptions about that layer. We can assume that it will be a 12-inch stabilized subgrade with an LBR value of 40, because that's a fairly standard stabilization we use here in Florida, because it provides a good working platform, and we'll be sure to specify it in the pavement design that goes into the plans. So looking at our layer coefficients table, let's find the coefficient for our stabilization that we've picked, which is listed here as Type B stabilization LBR 40, with a value of 0.08 per inch. So now we know our A4 value is 0.08 and our D4 value is 12 inches. So going back to our equation, let's fill those numbers in where they belong, and now we can move on to the next layer. So let's review everything we know so far. We just determined that we're going to call for 12 inches of type B stabilization. We also just looked at table 5.5 and found that based on our projected traffic, our minimum structural course needs to be 3 inches thick, and our minimum base group is base group 9. Since we know that our minimum base course will be from optional base group 9, we can calculate the structural value of that layer. Remember that the materials listed in a base group are all structurally equivalent, so if we look at the material thicknesses and structural numbers in group 9, we see that 10 inches times 0.18 gives us a structural value of 1.8. 12 inches times 0.15 gives us 1.8. And 6 inches times 0.3 also gives us 1.8. So the structural value of optional base group 9 is 1.8, and we can go ahead and plug that value into our equation. So now we have two of our own known values determined. Now let's look at our structural layer. We know that our structural coefficient is 0.44 regardless of the mix type. The contractor has the option to select from SP 9.5, 12.5, or 19.0 depending on the project-specific limitations and the requirements in the specifications. For our design purposes, we can see that each of those different mix types have the same structural coefficient. So the information we'll need to provide in the plans is the total thickness of structural course. So let's start with the minimum required thickness of superpave, which is 3 inches according to table 5.5, which we just looked at a few minutes ago. So now, we can plug those values into our equation, and we're left with just one layer to figure out. So our last layer we need to figure out, we have our friction course. Layer 1. For this example problem, let's assume that our design speed is 45 miles an hour. If we look back at our friction course policy table in Chapter 4, we know that we have two options for a multi-lane flush shoulder roadway with a design speed of 45 miles an hour. We could select FC 9.5 or FC 12.5. So let's look at another factor that will affect our friction course selection. Since our design ESOL was 12.6 million, we know that that's categorized as traffic level D. And if we read in the text of Chapter 4, just above Table 4.1, we see that FC 9.5 should not be used for traffic levels D or E. So for this example problem, we'll need to use FC 12.5 due to the projected traffic. So now that we know that our friction course will need to be FC 12.5, we need to determine the layer coefficient and thickness. Referring to Table 5.4 again, we see that FC 12.5 and 9.5 have the same structural value as our superpave courses. FC 12.5 and 9.5 are structurally equivalent to our structural courses, so our coefficient for our friction course in this example problem is also 0.44. Now to determine the thickness of our friction course. If you read Chapter 4 of the Flexible Pavement Design Manual, it tells you that FC 12.5 is typically placed in an 1.5 inch lift. So for a starting point in our calculations, let's go ahead and assume a 1.5 inch layer of FC 12.5. Now that we have all of our unknowns defined, it's time to crunch the numbers. So you can see the values we determined for each of our 4 layers here. So multiplying each layer, we get a calculated structural number of 4.74. Remember, our required structural number that we determined at the beginning of this example problem was 4.51. That's the number we obtained from the design table in Appendix A of the Flexible Manual. So as long as our calculated structural number is greater than our required structural number, we're good to go. But I want to note a word of caution. If our calculated structural number had turned out to be substantially more than the required structural number, we would have wanted to go back and review our design because it was extremely over-designed. This results in excessive and unnecessary cost to your project, so always look at the results and make sure they're reasonable. Now let's look at a few other design considerations beyond just the calculations. The first one I want to talk about is layer and lift thicknesses. Pavement design is really an iterative process, and there will be times when you'll be adjusting your structural course thickness to meet the structural number requirement. As you're adjusting your structural course thickness, you should design it to the nearest ½ inch. This is for practical and constructability purposes. While asphalt can be laid in 1/4 inch increments, ½ inch increments are preferable. The thinner the lift is, the quicker the asphalt cools, and if it cools too quickly, it may create compaction issues. So this brings up another consideration, that's lift thickness of a 9.5 mix, whether it's a structural course or a friction course. Although the specifications allow for a 1-inch lift of 9.5 mix, our recommendation is to try to avoid using a 1-inch lift if you can. In most cases, you can design around having to use a 1-inch lift by adjusting your other pavement layers. Just be sure, though, when you adjust your pavement layers, that you do not change the overall pavement thickness. And there's a few other requirements related to the structural course that I want to bring to your attention. For SP 9.5, which is our finer mix, you're limited to using this in the top 2 structural layers, and you can only use it for a maximum of 2 layers. Also, SP 9.5 should only be used for traffic levels A, B, or C roadways. This is all due to past performance issues with thicker layers of 9.5 mixes tending to rut due to their smaller nominal maximum aggregate size. The performance issues mainly stem from the Marshall mix days, and although our super paved mixes are certainly much better than the Marshall mixes, we still want to play it safe and limit the total thickness of our fine mixes. Also, for our SP 19.0, we do not use this mix in the top structural layer when we have an open graded friction course right above it. This restriction also dates back many years to the Marshall mix days, when we were seeing some segregation issues with our S2 mixes, which had a nominal maximum aggregate size of 19 millimeters. So when you have areas with segregation issues, you'll likely have greater permeability in your pavement, and so placing an open graded friction course on top of a layer that may tend to have a greater permeability would increase the chance of letting water into our pavement structure. So the decision was made at that time to limit the use of 19 millimeter mix directly beneath an open graded friction course, and we simply stuck to that decision. Again, our mixes are substantially better these days, and it may not necessarily be as much of an issue now, but our preference is to continue the practice of only placing SP 19.0 under dense graded friction courses. So once you finish the calculations for your pavement design, you'll need to sketch out the construction sequence of the typical section using the allowable layer thicknesses from the spec to ensure constructability. The example here is from a project where we have some milling and resurfacing of a main line, along with some new construction and widening. As you can see, the new construction and widening portion has a thicker layer of proposed structural course. This will not only provide the proper structural support for the pavement, it will also ensure that any future milling operation will not likely mill into the base material. Also notice that the final lift of asphalt, the friction course, has a uniform thickness of 1.5 inches, which means it can be constructed in a single pull. You'll need to make sure to include this sketch in your pavement design package. So now let's look at what your design actually translates to in a set of plans. You'll find the pavement design here on the typical section sheet. Notice that individual asphalt layers are not shown on the plan sheet. Only the overall asphalt thickness is called out. This is to allow the contractor options for how to construct the pavement. Let's say, for example, that the contractor has a pavement design that included a 3-inch layer of type SP structural course. Based on this table and the standard specifications, he could select to use 2 1.5-inch lifts of SP 9.5, or he could use 2 1.5-inch lifts of SP 12.5, or he could choose to use a single 3-inch lift of SP 12.5. It's up to the contractor to select the means and methods to construct the asphalt. Our job is to provide a thickness at an increment that meets the structural requirements of the project and is also constructible. Another design consideration is binder selection. The department's standard asphalt binder grade is PG 67-22, which means the binder should be rut resistant up to temperatures of 67 degrees Celsius and crack resistant down to temperatures of -22 degrees Celsius. There are times when a modified binder should be used, and these are discussed in section 5.4 of the Flexible Manual. As a reminder for Module 1, a modified binder is either a PG 76-22 or high polymer binder. So here are some instances where we want to specify a modified binder. You'll need to call for a PG 76-22 binder where an open graded friction course, so FC5, is used. In the top layer of structural course on roads that are traffic level D, which is a design easel range of 10 million to less than 30 million. It's used in the top 2 layers of structural course for traffic level E, which is a design easel of 30 million or greater. And it's used in FC 9.5 and 12.5 for traffic levels A through C, which is a design easel range that's less than 10 million. You should call for either PG 76-22 or high polymer for FC 12.5 in areas of traffic levels D or E. The reason FC 9.5 isn't listed here for this category is, again, because it's not used on these higher traffic levels. And you should also use either PG 7622 or high polymer in areas where you know you'll be having heavy and slow-moving loads, such as intersections and toll booths. The resilient modulus of asphalt is less under a slow-moving load than under a more dynamic high-speed load, which results in a higher potential for rutting, so that's why we suggest using the modified binders in these areas. Since stabilized subgrade has a history of good performance and provides strength to the pavement system at a low cost, it's highly recommended that a stabilized subgrade element be included in a pavement design. However, in some situations, project conditions may dictate the elimination of a stabilized subgrade during design, and so you'll need to achieve your required structural number with just the base course and asphalt courses. These conditions might include limited working areas such as intersections and medians, shallow existing utilities that are impractical to relocate, and areas of urban projects where it's essential to accelerate construction to limit restriction of access to adjacent businesses. Stabilized subgrade should not normally be eliminated over extensive areas, because it's necessary to provide a working platform for base construction operations. This is an especially important consideration with asphalt base course because of the difficulty in achieving compaction of the first course placed on an unstable subgrade. The district construction engineer and the district materials engineer should be consulted prior to deciding to eliminate stabilized subgrade in design. The reasons for eliminating stabilized subgrade must be documented in the project file. In general, the options for base material should not be restricted. Allowing the contractor the full range of base materials will allow him to select the least costly material. Unbound granular base materials are generally the least expensive. However, the following conditions may warrant restricting the base course to an asphalt base course, which is designated as type B12.5 or otherwise known as black base. In an urban area, maintenance of access to adjacent business is critical to the extent that it's desirable to accelerate base construction. The maintenance of traffic scheme requires acceleration of base construction in certain areas of the project. High groundwater and back of sidewalk grade restrictions make it difficult to obtain adequate design high water clearance from the bottom of a thicker lime rock base. The thinner asphalt base can help increase the clearance. Note that asphalt base requires a well-compacted subgrade just as lime rock base. It's usually necessary to have 2 feet of clearance above groundwater to get adequate compaction in the top foot of subgrade. In areas where this cannot be obtained, the district drainage engineer should be consulted for an underdrain design or other methods. The configuration of base widening and subgrade soil conditions are such that accumulation of rainfall in excavated areas will significantly delay construction. And finally, a decision to restrict base course material to an asphalt base course throughout a project must be documented and approved by the district design engineer. This concludes Module 4, Pavement Design Process for New Construction.